Hi class, we are now on chapter 14 and this is oxidation and reduction. This is a challenging topic. I know most of you are saying, probably thinking chemistry in itself is, but as you have learned, some are a little bit more challenging than others. And this is one of the subjects that students tend to have a problem with. So I just want to put it out there. It's not impossible, and I'm going to tell you right now, if you learn the rules, it will not be as overwhelming. And that's the problem, is that if you don't understand the rules, it's overwhelming. And I'm gonna go through the rules, and I'm gonna show you an example of the rules. And as long as you can learn the rules, you can handle this. Okay, so in the year 1800, the Italian scientist Alessandro Volta created the first battery. This invention changed the world and kicked off the field of electrochemistry, the study of chemical processes that involve the movement of electrons. To understand electrochemistry, we must begin with a class of reactions called oxidation reduction reactions, also known as redox. Redox, R-E-D-O-X reactions. It's just an abbreviated form of saying oxidation reduction. We briefly introduced oxidation reduction reactions in chapter 6. In this type of reaction, one species loses electrons while another species gains electrons. The loss of electrons is called oxidation. When a species loses electrons, we say it has been oxidized. The gain of electrons is called reduction. When a species gains electrons, we say it's been reduced. So let me give you an example. This is not necessarily an oxidation reduction reaction, but I want to give you an idea of what this means. So let's say sodium chloride. I want to give you an example with something we understand, even if it's not specific to oxidation reduction. You'll understand these definitions this way. Sodium chloride is an ionic bond. So sodium, it goes from a 0 to a +1 when it loses its electron, because it goes into ionic form. So when it loses that +1, it becomes a +1, it is oxidized. It lost electrons. It changed the oxidation state to a +1, so it's been oxidized. Now that electron, if you follow that electron, it goes to chloride. So chloride goes from a 0 to a -1. It's been reduced because it gained that negative charge, and now it made it a -1. So it's been reduced down. So it took in an electron. So it's like a catcher and a pitcher. The pitcher throws the ball to the catcher, and the catcher keeps the ball in this case. We're following where the electrons go based on the oxidation state. Now hopefully that makes a little bit of sense here. So let's take a look. This is a reaction we're going to come back to. When dealing with simple monoatomic ions, the gain or loss of electrons is easy to determine. However, many redox reactions involve polyatomic ions or neutral molecules, and the change takes place on each atom can be harder to, let me start that again. However, many redox reactions involve polyatomic ions or neutral molecules, and the change that takes place on each atom can be harder to measure. For example, consider the reaction of sodium metal with water, written as an ionic equation. In this reaction, the sodium is oxidized. It loses an electron, but what is reduced? That is, which atom gained the electrons? At first glance, this question may be difficult to answer. Scientists use oxidation numbers to keep track of electron changes in redox reactions. Oxidation numbers do not necessarily reflect the actual charge on atoms. Rather, they are bookkeeping tools to ensure that the overall electronic changes are accounted for. Before we answer this question, let's look at the rules for assigning oxidation numbers. So it is a reaction that we know just by looking at. We can see that sodium lost an electron, but where did the electron go? And by looking at it, we can't simply see it. We can see that there's some changes, but we really don't know what happened to it. And that's where that's what the bookkeeping is. By looking at oxidation states, we can figure out where that went. Okay, so let's take a look. Here are the rules, and these are specifically what I'm saying you need to learn. You need to learn them. You need to memorize them. They are what this whole section's about. This is the foundational portion of learning this chapter. So the oxidation number of any species in its elemental form is 0. That means its natural state. So let's take a look here. Do you see sodium is a solid? It's by itself. In its natural state, it's a solid. So that would be a 0. Something like oxygen, O2, as a gas, that's in it found. Diatomic gas, the molecules are found as gases. So hydrogen, H2, O2, F2, Cl2, these are all found in their natural states. Even though they're gases, they would be assigned to a 0. If you find metal by itself, so iron by itself as a solid, that would be a 0. So anything in its elemental form, not when it's combined with something else. So don't see a solid and think, okay, it's a solid, it's a 0. No, no, no. That's where we're tracking stuff. But when it's by itself in its natural form, so iron by itself, O2, H2, those are what we're looking at. Monoatomic ions. The oxidation number is simply the charge of the ion. This rule does not apply for all, not even close. However, ones like group 1, those are all +1. So those are pretty easy. So sodium, as we're looking at it, would be a +1. That doesn't change. Chloride would be a -1. So some of these are really easy because it's group 1. We can automatically determine potassium, lithium, those are all +1. Polyatomic ions. The oxidation number of the atoms must add up to the overall charge of the ion. So for neutral compounds, the oxidation numbers must add up to 0. So what do I mean? For right there, for we look at water, everything there, we're going to break this down. The oxidation states for those must equal, when added together, a 0, because that water is a 0 neutral compound. But when we look at hydroxide, that's a polyatomic. So when we look at the oxidation state of that, that must equal -1, because it's got a -1 charge on the polyatomic ion. That's what that means. So I'm looking now at number 4. Atoms and molecules are polyatomic ions. The oxidation number of fluorine is -1. The oxidation number of oxygen is -2. Now, in this case, it's when oxygen is combined with something. It's a -2. When it's O2 by itself as a gas, it's a 0. And the lower halogens, chlorine, bromine, and iodine, have an oxidation number of 1. Unless they are bonded to oxygen or fluorine, then they become actually a positive number. They become a positive of their charge because they are now dealing with a more electronegative atom, oxygen and fluorine. They become the cation in the sense, and oxygen and fluorine stay with what they have. In compounds of hydrogen, hydrogen has an oxygen number of +1 or -1. If a hydrogen is bonded to a nonmetal, it's assigned a +1. If it's bonded to a metal, it's a -1, and then it's known as a hydride. Okay, so let's plug these numbers in. Okay, so let's look at this. To see how oxidation numbers work, let's analyze the equation we introduced. We begin by finding the oxidation number for each atom present. So basically, just start where the sodium is and go down. Don't even worry about where the electrons are going. Just put the oxidation states. So in this case, sodium is a solid, and hydrogen gas on the other end is a diatomic. It's diatomic, so it's found in its natural state. So in this case, you have a 0 here to account for the elemental form, the natural state. This matches rule number 1, which says in elemental form, oxidation is 0. Same as here. It's 2 of them, so that's why you see 2. It's accounted. You have to count for everything, so this is a 0 and a 0. Okay, so for monoatomic sodium ion, we can see here it's a +1. And that matches its charge. Not always. It tends to be the transition metals that don't. But this one here is a +1, so we can write a +1 above it. And there's 1, so that's fine. So it's been oxidized to +1. For water, it's a neutral compound, so the charges that we're going to put for the oxidation states have to equal. So we have a hydrogen. It's a +1 because it is, remember the rule, it's bonded to a nonmetal. So it's a +1. Well, we have 2 of them, so it's a +1 and +1. And oxygen is -2. So that's where the -2 comes from. If you add these and these together, it's a 0. That works. So now let's go over here. Again, it's a -2 for oxygen, and we have a +1 for hydrogen. So this equals -2 + 1 equals -1, which matches the negative charge on the polyatomic ion. That works. Okay, so in this reaction, the oxidation number of sodium changed, and it's kind of good to draw what the ones that you're focusing on underneath, because then you can pull it out of the numbers. So we can see it changed from a 0 state to a +1 state. So that means that it lost an electron. It's been oxidized. But where did that electron go? And by looking at the reaction without any of it, we can't really tell. So in this case, we got to follow the oxidation states. So what we notice is that the oxidation number of hydrogen changed from a +1 to a 0. And the hydrogens gained the electron and they have been reduced. So the hydrogens from the water were ended up being changing to a hydrogen gas because the electrons, it gained the electrons. So it was reduced and it ended up resulting in hydrogen gas. Sodium gave up the electrons, hydrogen took them, and that's where the produced as a hydrogen gas. Okay, so let's move on to another one. Let's look at another example. Identify the oxidation number for sulfur in the following 3 species. So for monoatomic ions, the oxidation number is simply the charge. So in this case, when it's by itself, mono meaning 1, it's the charge it is. So in this case, it's a -2, which remember, it's also underneath oxygen. So it's a -2, so it's similar to the oxygen. But when we look here, we have SOCl2. This is a neutral compound, so everything here has to equal 0. So let's make S as X. So this is where it gets a little confusing for students at first. This is where you have to use the rules. We want to know the oxidation state, and the oxidation states are not always what we know them as. For instance, this is -2. As you can see with the answers, it's not going to be that way. So let's pull these out, and what you do is you add them all together. So let's say X is S, so we have an X. And we have we have 1 oxygen, which is -2. And we're adding them, so we're adding what's by itself and multiplying how many. So we have X minus 2 plus we have 2 chlorines, which are -1. So that's where you see this, and everything equals 0. So if you add all this together, what you get, you can see here that we have a X minus 2 minus 2, which ends up being -4. But when we pull the -4 to the other side, it's a +4. So X equals +4. So in this case, the sulfur has an oxidation state of +4 in this compound. Now let's take a look at the other one. We have hydrogen sulfate ion, and has an overall charge of -1. So we have to account for that -1. So instead of making this all equal to 0, we make it equal to -1. And we do the same thing. Hydrogen is a +1. We have an X to represent sulfur. And then we have a plus sign because we have to multiply in with the oxygen. So we have 4 oxygens with the oxidation state of -2. Add everything together. Move it onto the other side. So let's see what this is. We have a -8. Plus 1 is -7. But when we move it over, it's going to be a +7 minus 1 equals +6. So in this case, the sulfur was a +6. This is algebra. So don't let it get overwhelming. Follow the rules, assign it to what it is. You will not always know the oxidation state for some of them, for instance, in sulfur in this case. But you will have enough of the rules that you'll be able to solve for it. And that's what you just did. So that's what I'm saying. As long as you follow the rules and do the algebra math, you will be fine. Okay, so let's look at another one. Find the oxidation number of each atom in the following reaction. Identify the species that is oxidized or reduced. The oxygen in O2 in an elemental form, as you can see right here, is 0. So we write a 0 above it. And the compounds of CO2 and H2O, the oxygen has a value of -2. So we have 2 of them, so it's -2, -2, and then here we have a -2. Okay, now each hydrogen in methane and water has a value of +1. So we have 2 here, so it's +1, +1. Here we have 4, so +1, +1, +1, +1. Okay, so so the only thing we need to look at now is carbon. In methane, the carbon must have a value of -4. Why do it has to have a value of -4? Because it's a neutral compound. So if we know the rules for hydrogen, then it must be a -4 because -4 plus 4 equals 0. So we assign it a -4. In carbon, we see that oxygen has a -4 because -2 and -2, excuse me, I don't like that they do it like that. What I do is I write a -2 times 2 is -4. And that means that this has to be a +4 in order for this compound to be neutral. So here, what we notice for oxygen, oxygen went from a 0 to a -2. So you see it's a 0 and a -2 and a -2. So it was reduced down. It went from, it gave up electrons. It gave up, it was reduced. It gained electrons. See, even I could get confused. It gained electrons from a 0. It took in 1 electron, which made it negative, then took another electron and another made it -2. So it was reduced down. So where did those electrons come from? Well, carbon was oxidized. It went from a -4 to a +4. So it lost a lot of electrons because it even had to get to 0. So it lost 4 electrons here. It went just to get to a 0 state, and then it lost more electrons. So this reaction, the oxidation number of oxygen changed from 0 to -2. The oxidation number of carbon was changed from 0,4 to +4, and carbon was oxidized. So in this, what this is, you had to identify what was oxidized and what was reduced, and we did that. So this is where the oxidation numbers come in. So you can see what was reduced and what was oxidized. Now, one thing is that some of these don't change. So if you see here, hydrogen didn't change. It's a +1 here and it's a +1 on this side. That's what will happen in a lot of the reactions, is that some of they're kind of spectator ions. You see their oxidation states, but they don't change. If they don't change, then you're not focusing on them. There's got to be something else that gained or lost electrons. Okay, so let's do a review here. Oxidation, the loss of electrons, something that loses electrons is oxidized. Reduction, the gain of electrons, something that gains electrons is reduced. These are redox reactions. Okay, and here's again the rules, and let's go through them. Now, I wrote on this, so you're going to see my lovely writing. I have horrible writing. I tried to write as clear as possible, so forgive me if it's a little messy. So here are your reactions, and here's my writing. So let's go through the first one, and I know it's a little busy, but so here is, let's just go through. So try not to focus on these, even though I know it's a little busy here. So the first reaction here, it's in its natural state. So silver is a metal, so that's where you get the 0 from. F2 is a diatomic gas, it's a 0. But as it's combined, something happened. What happened? Well, electrons were taken from one and the other one gained them. So in this case, we have silver that is a +1, and we have fluorine that's a -1. So what happened is that silver lost its electron, and in this case it matched the charge of it, and fluorine took the electron for this compound to actually be produced. So again, these seem a little confusing in the beginning, but focus on the rules, and some of them don't change in the oxidation state. So silver is a +1, that was really easy. Fluorine, the rules show you here it's a -1. So even if you didn't know that this was a +1, you know that this is a -1. This has to be a neutral compound. So if this is a -1, this has to be a +1. And the answers are right underneath. Okay, so let's look at this one. Sulfur by itself is a 0. Oxygen as a diatomic gas is a 0. So now we've got to solve for this one. So the one that you do know is oxygen. Oxygen is a -2. What we don't know what is sulfur. So this is going to have to be handled like this. You're going to have to solve for sulfur and plug everything in. And if you look here, I didn't show it on here, but I actually did do it on paper. I just didn't have room to show you. So you make S 0 and you solve for it. And if anybody has problems with any of these, let's go through them. But you solve for it. So in this case, the answer ended up being +6. So if you solve for this, make sure you get a +6 on sulfur. And how is that going to work? Well, if this is a -2, then this is a -2 with 3, that's -6, and then this is +6. So they cancel each other out. It's a 0. And then here we have a bottom one where I was showing you how we got -4. And carbons tend to be -4, 0, or +4. And in this case, this is a -4. Why? Because we've got 4 +1s. So it has to be a -4. This is a 0. This is a +4 because it's got to balance out the oxygen. This is a +1, and this is a -2. And in this case, these, hopefully, if you go through, you can see where I've got these numbers from. Go back to the rules. If the rules don't give you for one, such as sulfur, you're going to have to solve for it. Okay, so this is sulfur. I want to show you how I got sulfurs, +6. So this is this problem in the middle. So I made 2SO3 equal to 0, and then I started plugging in the numbers. So I have a 2S, but I also have a 2 with the oxygen. So I pulled it out. So it's multiplied by this and multiplied by this. And then I'm going to plus everything. So 2S plus 2 times 3 times -2. Where did the -2 come from? Because it's oxygen, but we have 3 of them. So it's 2S minus 12. I bring the 12 over. So now it's 2S equals 12. Divide by 2, S equals +6. So hopefully this makes sense. This is algebra at this point. Okay, identify the oxidation number. Oh, is this a repeat? I think I repeated on it. Oh, I broke it down. So that's what I did, is I broke it down, and it said to circle, but I didn't. It's already been, it's telling you which ones they are, so I didn't do any of that here. So, but I did show you how I solved for this. So you can see here it's 2 plus 1 plus 2 minus 1 equals 0, and this is the one that I was doing here. On the other one I did here, we solved for this, so it's 2 plus 2, and in this case it's 2 minus 2. Where did the plus 2 come from? Well, if oxygen is -2, this has to be a +2 to cancel it out. And then here we have methane. This is a -4. We have a +1, but there's 4 of them. And then we have a 0 for the oxygen, which is a natural state. We have a +4, and here we have a +1 and +2. What you're going to notice is that I know some of these are repeat problems, but the atoms in them don't really change the oxidation states. You'll start plugging in and go, oh, I know that this is a +1. Oh, this is a -2. The ones you don't know, those are the ones you're going to have to solve for, but it's algebra. And if you stick with the rules of the ones you know, you'll be fine. Okay, so what is the oxidation number of phosphorus in this ion? So now we're going to do algebra. We're going to plug it in. So make sure that you make the -3 on the other side of the equal sign. We don't know what phosphorus is, but we do know what oxygen is. So we do P plus 4 times -2. That ends up being P minus 8 equals -3. We take the 8 to the other side, and P is a +5. What is the oxidation number of carbon in this compound? So now we want to know carbon. This is a neutral compound, so this should be with a 0. So now we plug everything in. We have a sodium, which is a +1. We have hydrogen, which is a +1. We don't know what carbon is, but we know what oxygen is, and we have 3 of them with a -2 charge. Do this math to it. So we have 2 plus C minus 6 equals 0. So we bring everything over to the other side, which is C equals +6, -2. So C equals +4, and I put in parentheses, carbon is usually -4, 0, or +4. What is the oxidation number of iodine in this compound? Same thing, we're going to make it equal to 0. We're going to plug in what we know. So potassium is a +1. We have iodine plus oxygens that we do know. So 4 times -2. That's iodine +1 minus 8 equals 0. So now we have iodine -7. After we've done the math, we bring that over, and iodine is a oxidation state in this compound of a +7. What atoms are oxidized in this reaction? So in this case, you have to do the math. You're going to have to go through and follow and see what happened to it. And in this case, it's A. A has been oxidized. And you can see I put the oxidation states above it so you can see what happened. What species is oxidized in this reaction? So again, we put the oxidation states, we go above, and you can see that magnesium went from a 0 to a +2, so it lost 2 electrons. What species is oxidized in this reaction? So again, do the oxidation states, plug everything in, and you can see that nothing changed. And that means that this reaction right here is neither a reduction or an oxidation reaction. By the way, when something is oxidized, something else has to be reduced down. So we're not focusing on what's being reduced down, but you can't lose electrons and have them sit idly somewhere. There has to be a reduction in it. So they go hand in hand. If something's oxidized, there has to be something reduced. If there isn't, then it's not an oxidation reduction reaction. And in this case, none of the oxidation states change. This is not an oxidation reduction reaction.